Have you ever just stopped and wondered how AI like ChatGPT seems to just get you? It feels like magic, right? Well, it's not magic, but it is an incredible stroke of genius. Today, we're going to pull back the curtain on the one mechanism that makes it all possible, the thing that allows AI to truly understand context. It's called attention. All right, let's start with a really simple problem that used to totally stump older AI, the word apple. You know, if you say, I'm eating an apple, you mean the fruit. But if you say, I'm coding on my apple, you mean the computer. For us, that's obvious. But for a machine, how in the world does it figure that out? You see, the whole problem boiled down to this. Old school AI had this super rigid way of looking at language. It saw a word, and it gave it one and only one meaning. And as you can probably guess, that led to some serious mix-ups. So in these older systems, every word gets turned into a list of numbers, what we call an embedding. But here's the catch. That embedding was totally static. So the word apple had one single numerical identity, and it was always hanging out with words like orange and banana. Now, that's fine if you're making a grocery list, but it completely falls apart if you're trying to talk about technology. So what was the big breakthrough? It was this incredible mechanism called self-attention, and the name is just perfect, because it is literally about letting the words in a sentence pay attention to each other to figure out the context all by themselves. And here's the most crucial part. Self-attention takes that static, one-size-fits-all meaning and makes it totally dynamic. It's what allows the meaning of apple to literally change depending on the other words around it, words like eating or coding. This whole idea wasn't just some theory either. It came from a landmark 2017 paper with the boldest, most perfect title you can imagine. Attention is all you need. And that paper? It introduced the world to the transformer architecture, the very foundation that pretty much all modern large language models are built on. Okay, so to really get how these words talk to each other, let's use a little analogy. I want you to imagine that every word in a sentence is a person at a big networking event. To figure out who to talk to, each word takes on 3 different roles. First up, you've got the query. Think of this like a word raising its hand and basically shouting across the room, "Hey, I'm the word it over here. Is there anyone in this sentence who can help clarify what I'm referring to? Anyone?" And in response to that query, every other word in the room holds up its key. The key is just like a name tag. It proudly says, here's who I am and here's what I'm about. The original word then scans all of these name tags, looking for the absolute best match for its question. And then, once a really strong connection is made between a query and a key, the word with that matching key shares its value. The value is the good stuff, the actual information, the substance that helps the original word update its own meaning based on this brand new context. And would you believe it? This whole conversation is really just this beautiful 4-step mathematical dance. First, the model calculates a score to see how well a query and a key match up. Then, it scales those scores down just to keep everything stable. Third, it weights them, turning the scores into simple percentages. This tells the model exactly how much attention to pay to every other word. And finally, it combines all the juicy information, the values, from the most important words to create a brand new, context-rich meaning. It's just so elegant. And check this out. This is what it looks like in practice. Take the sentence, the animal didn't cross the street because it was too tired. The word it has to figure out what it's talking about. So using attention, the model calculates how relevant every other word is. And look at that. It gives a massive 85% of its attention weight to the word animal. It figured it out. It correctly made the connection, all thanks to that simple mathematical process. So that's the basic idea. But of course, it doesn't just stop there. This core concept has been beefed up and adapted into even more powerful versions to tackle even trickier problems. So first you have what's called causal attention. Now, standard attention lets a word look at everything, past and future, but causal attention is way stricter. It only lets a word look backwards at the words that came before it. And this is absolutely critical when you're training a model to generate text, because it stops the model from cheating by peeking ahead at the right answer when it's supposed to be predicting the next word. And then you've got multi-head attention. This is like running a whole bunch of these self-attention processes all at the same time, in parallel. Think of it like a team of specialists all analyzing the sentence at once. One head might be an expert in grammar, while another focuses on the deeper meaning, and a third is amazing at spotting connections between words that are far apart. Altogether, they build this incredibly rich, nuanced understanding of the text. It's how AI starts to grasp things like sarcasm or even metaphors. Okay, so where does this amazing mechanism actually live inside a real-world model, something like GPT-2? Let's zoom out and take a look at the big picture. This is a super simplified look at a single decoder block, which is the fundamental building block for models like GPT. And notice what happens right at the beginning. Step 2, multi-head attention. It's not some afterthought, it's right there at the very heart of the process, figuring out all the context before anything else even happens. But here is where the scale just becomes absolutely mind-boggling. A model like the small version of GPT-2 doesn't have just one of these blocks. No, it stacks 12 of them, one right on top of the other, with the output of one feeding directly into the input of the next. And believe it or not, it gets even more complex. Inside each one of those 12 layers, there isn't just one attention mechanism. There are 12 parallel attention heads, all working at the exact same time, each one hunting for different patterns and relationships in the text. And all of this insane computation across 12 layers, each with 12 heads, is happening over a sequence of 1,024 words or tokens at a time. The processing power needed for this is just staggering. It actually grows quadratically. That means if you just double the length of the text, you need 4 times the computing power. It just explodes. And that's it right there. This massive, massive scale, the layers, the heads, the huge context windows, all driven by this attention mechanism. That is what puts the large in large language models. It's the source of their incredible power to understand and generate text that feels, well, human. Which leaves us with one last truly fascinating question. We know that each of these hundreds of attention heads learns to specialize in some unique linguistic pattern. So as we build bigger and bigger models with thousands, maybe millions of these heads, what are they really discovering about the fundamental structure of our language? And maybe, just maybe, what are they showing us about the structure of human thought itself?